Thank you very much. Okay, so I'll just see if this works. It doesn't work. Okay. Thank you very much for the invitation, Can, and it's great to see you all here. So my name is Mehmet Cengiz Onbasli, and I'm a faculty in electrical engineering and physics. And I have been working on skyrmion dynamics and magnetic thin films. So I'm going to Okay, is that now better? All right. So I'm going to today present to you about skyrmion dynamics and the analysis of the route to reach ultra-low energy logic and memory devices. So I'm an experimentalist, but today I'm going to present to you some of our modeling work, which could lead to some potentially interesting routes for applications with devices. So if you want to dig deeper into what I'm going to talk today, you can look up the papers that I listed here. So these are the papers that we have had published over the past few years. So I would like to thank my grad students, Arash, Ravana, and Saide. So they have been doing the modeling work, and also PLD growth. So we have recently started PLD and just put together the MBA system just 2 months ago. So it's going to start doing some topological insulators and TMDs. And in the meantime, we have also been doing micromagnetic modeling, which I will talk about today. And we have been collaborating with theory groups and also other different experimentalists for growing new functional devices. So today, the main purpose of this talk is basically establishing a route for ultra-low power magnetism. So magnetism actually is a very interesting set of phenomena because it provides us routes for achieving ultra fast dynamics. Meaning, if you can eliminate all these terms throughout the Gibbs free energy, you can actually reach exchange-driven effects which happen at the femtosecond rates. So when we look into the Gibbs free energy of an arbitrary system, we can actually talk about the expansion, volumetric expansion, or magnetic field effects, or electric polarization induced effects. And for the sake of data storage or logic processing, we can think about this gap as one of these terms or multiple of these terms contributing to our switching mechanisms. So in this kind of a switching mechanism, you can envision ferroelectric systems or memory-stive effects or soft polymers which basically have the PV and entropic changes, or magnetic systems that can have voltage-controlled magnetic anisotropy or magnetic field contributions in the Gibbs free energy. So all of these terms can be tuned depending on the material choice or the system architecture. But by eliminating each term one by one through the device geometry or through material choice, one can all come down to a common aspect, which is the entropy. So we can never exceed the entropy term. We must have it. So that's why the entropic limit, so excuse me for that. So the entropic limit is actually always there. So that means we would have to really get the entropy term as our baseline. So once we have the entropy baseline, that means we can think about, okay, thank you. We can think about encoding our information with this barrier of entropic limits. So if we ignore all other terms, we always have the entropy. So if I have an entropy difference of the K times LNW, which is the number of configurations that we can have. For instance, let's think about spin up versus spin down states for encoding information. Then we would, in the lowest limit, we would have K LN2, which is our number of configurations. This is the minimum. And in this case, the entropy becomes simply K LN2 entropy difference. And the TS term then becomes our ultimate barrier, which is basically the LANDAU limit. So one can potentially eliminate all energy contributions and come down to all the way down to the entropic term. So, but there are ways to achieve this. So in today's talk, I'm going to motivate some more aspects through the other end, which is the direct application. Some of the talks were about applications, but now I'm going to talk from the other end, which is the computing aspect for the requirements that are imposed. So in this case, let's talk about the von Neumann architecture. People have been talking about this quite extensively. So one of the interesting aspects in today's computers is we have quite a bit of buzzwords going on, like Moore's law, scaling of transistors, and so on. But what happens is we receive an input, we process those inputs, and then feed it back to the memory. And based on the commands, we keep on receiving inputs from the memory, process, feed it back to memory. And as the requirements of machine learning driven applications or sensor driven applications increase, we always face this bottleneck from the memory bandwidth. So the memory bandwidth has to really be resolved through in-memory computing. So this is the whole point that I'm going to focus on. So people have been extensively studying all these architectures, but this is going to be one of the issues in the scalability of future computers. So let's move on to what can be done to eliminate this. So you may have seen this figure in one of the reviews. The idea is we can encode information into spins or orbital angular momenta, or their sum, or even charge. So this is useful, and it can also be coupled with macroscopic quantum effects, or we could also extend the operation frequencies. But most of the device applications which rely on spin waves or skyrmions don't necessarily directly use the non-volatility of these films. So that's why there needs to be some means for using the non-volatile aspect to save power, and also using non-conducting layers like insulators or semiconductors for eliminating joule heating. So to do this, multiple architectures have emerged, and the purpose is to reduce the delays between the processor and the memory, and converge them at the register level. So ultimately, exchange-driven spin time scales, spin relaxation time scales will be our driving force. So if we can approach femtosecond limits through eliminating different anisotropy terms, that could lead to our ultimate limits. So the whole purpose that I'm going to present to you today about our results will be different from the anisotropy or the spin orbit torques that our experts here already demonstrated previously. But here I would like to focus more on how we can use non-volatility through the skyrmions. So I'm going to directly go to the anisotropy terms we use for essentially using skyrmions to construct spin logic devices. So you all know LLG equation, and the LLG equation terms here include exchange, external fields, the Zeeman terms, Dirac fields, uniaxial anisotropy, and Jolshinsky-Moria interaction. And we are using current-driven effects to construct a geometric constriction-driven geometry to see how much we can reduce the consumption requirements of our systems. So here we provide the cross-shaped geometry where we provide the logic input for skyrmions. The presence of skyrmion is encoded as 1, and its absence is encoded as 0. And we provide a periodic stream or arbitrary stream of probing skyrmions to see the presence at the output, which is this part. And the interesting part that I'm going to show you later is that this geometry can be used as a flip-flop for using the logic gates. Previously, most of the logic gates in skyrmions were not actually used for the non-volatility aspects because the control of skyrmions is challenging in the experimental side. So let me show you some of the micromagnetic model results that we have for essentially our logic inverter gate. which consists of cobalt platinum bilayers. And here we don't have any external magnetic field. We only drive with current. So in this case, we first push with current and then convert skyrmion into a domain wall. And then this domain wall fills the channel. And this domain wall can actually encode the previous state of the system as well. This way, we could read out the next state or the previous state from this memory element. So it can actually deliver 0 here. And we do a clearance pulse to clear for the next clock cycle to achieve a clean slate for our operation. For the next side, we do have the 0 input, which means there's no input from the logic input side. And we simply probe, and the probe propagates without any barriers. Of course, there is some demagnetization field barrier here. And this actually becomes relevant, especially at room temperature models. And in the room temperature models, we observe that there can be a statistical nature as long as we don't increase the anisotropy terms of the system. So the stability really relies on the anisotropy terms that we play around with. So I show you the time scales of these operations right now. So these are right now nanoseconds or few nanosecond levels with currents on the order of 10 to the 12 or high 10 to the 11 amps per meter squared. And we do have a pulse stream that basically determines how this can operate. So initialization is essentially the first step with which we prepare the logic. And then we do a transmission step, which is for retrieving the output. And then we can decide to do clearance to prepare our logic gate for the next step. So we looked into the current density dependence of the initialization operation, and it actually drops as one can intuitively expect with current. And with more current, there's also going to be a faster operation for the pastime of this middle step. And of course, magnetic field assistance can also accelerate the operation times down to several hundreds of picoseconds. So, of course, the orientation of magnetic field really matters because of the signs of the anisotropy terms. And at the end of the day, we can find a balance that could lead to sub-nanosecond operation. So the important thing that I want to bring out here, and I would like to tie it back with the Landau limit picture, is that when we look into the magnetic energy, total magnetic energy of the system as it is evolving over time, we actually observe that introducing skyrmions or deleting them actually costs some magnetic energy. So in this case, we really have to put in some energy. And those are the inputs that we use for consuming the energy to store information. So information is physical, at least in the entropic sense. And because we are using metallic layers for this demonstrator here, we need to essentially consider Joule heating and magnetic energy separately. So when we consider Joule heating, it's actually 4 orders of magnitude larger than the magnetic energy. So this points out the fact that Joule heating can become the showstopper for these kinds of devices. So once one can substitute these kinds of devices with semiconductors or insulators, the energy consumption can really drop by 4 or 5 orders of magnitude. In addition, once we cascade these devices, the device scaling and the power consumption scaling actually is linear. So as we cascade with more devices, we simply increment with the number of devices for the operation. So I'm not going to show here today the rest of the logic gates that we have designed, but cascading and achieving other types like AND gate, OR gate, or cascading them all to achieve, for instance, if-else structures for digital design can actually be established. So here I would like to move forward with a periodic signal generator for skyrmions. So here, a geometry basically can be used to trigger periodic stream of skyrmions that could act as a clock source or some form of a prober for the logic gate architectures. So when we consider the magnetic energy differential for each skyrmion generation, it turns out 67.5 kb LN2 is what we get for the room temperature case. So this is the 0 Kelvin results that I'm showing here for ease of operation and for simulation time. But it boils down to this kind of an energy level. And this is the operation steps that we can look into. And the idea is by tuning the DC current that we drive with, it's a spin polarized current, and by tuning the spin polarized current density, we can actually play around with the rate at which these are generated. So the skyrmion generation rate actually can act as a voltage controlled frequency generator. So these kinds of device architectures can actually resemble some of the RF components where people were interested in frequency generators through different voltage knobs. And the scaling is not too bad in that we can achieve reasonable rates that would not burn the device. So the scaling goes from 100 megahertz till 20 gigahertz, but this is modeling, so we haven't yet experimentally demonstrated it. So the operation actually relies on some initialization where we need to convert skyrmion into a reservoir domain structure. And then, depending on the instabilities of these reservoir structure, we keep on kicking out skyrmions from the generation step. So this is the initialization step can be done only once, and then clearance and generation can be done depending on the application steps. So the main handles here that determine the operation are current density and damping. Because if we have a very large damping, it essentially kills the dynamics. But if it is too slow, then we don't get to have the stability either. Because cases 2, 3, 4, 5 actually indicate that we cannot easily nucleate out our domains or skyrmions. So that's why a balance of these damping parameters and current densities is critical. So finally, let me wrap up the whole picture and come to a direction where one can actually investigate. So the idea is, of course, we need to reduce the power consumption through eliminating joule heating. That's one of the main steps. The next step would, of course, be achieving higher frequency operation through the increase of current. But the current actually is not our friend here because it also can destroy the skyrmions or domain structures. As a result, we would really have to play around with the anisotropy terms for our 2D layers. And of course, once we cascade these devices, the microelectronic integration would really become an important parameter, especially the impedance matching and geometry mismatch would really be a big driver that one needs to pay attention to. With that, I would like to thank you very much. And if you have any questions, I can take them.
Thank you for your presentation. So my question is that especially for the first logic device design, what would be the error rate? Have you calculated experimentally or via simulations?
So the error rate at 0 Kelvin is essentially 0 because it works always.
For the room temperature?
At room temperature, it is on the order of 10 to the minus 4 or less. But of course, one needs to play around with the anisotropies to make sure that error rate is less than 10 to the minus 9. Because in a regular telecommunication channel, you would observe 10 to the minus 12 or less for any meaningful operation.
Thank you.
Thank you. The temperature.
And you dissipate everywhere.
Oh yeah.
But in the end, temperature is also useful to nucleate skyrmions, to deepin them.
Oh yeah.
So why don't you like it?
So in many cases we rely on the, for instance, in this reservoir case, we rely on the domain wall pinning mechanisms. So if we rely on those pinning to the walls of the structure, then temperature can be the culprit that detaches from the geometry. So, but one can play around with the symmetries of the geometry to ensure that temperature can play in our purposes actually. So that's a good suggestion. So I should really actually play into that part. Thank you. Yeah.
One thing is that you mentioned that if you use insulator, you can decrease the energy consumption by order of 10 to the 4. So, but if you still rely on spintronic force, so how would you achieve that? You still need to have current for that.
Exactly. So that's one of the challenges. So that's why I'm showing you some concept figure that shows a surface that contains the interface between a non-conducting TMD with a TI or some TI with another kind of layer that is not metallic. So that's the purpose that I'm trying to demonstrate here.
So you rely on it to the conduction.
Through the conduction channel, it's essential. Otherwise, exactly. And of course, it would bring more questions than it answers probably, because you would have to rely on the Fermi axes, which would cause ballistic transport, different torques, and it would cause domain wall pinning and all these kinds of effects. And the anisotropy terms and dampings would also change dramatically. So the equilibrium condition for device stabilization would also shift as well.
And then you give the numbers in current density, so where you exactly take the device? The geometry is very irregular.
Exactly. So so let me get back to the current density calculation. So we calculate from the entrance, and then for the cases for constrictions like these, we calculate them with extra reduction in the cross section.
The number that you're giving is for the outside part.
Exactly.
So there it gets much higher.
Right. So that's one of the bottlenecks of these calculations. So we really need to reduce the consumption by either using, for instance, synthetic anti-ferromagnetic skyrmions, or by substituting at least one of the cobalt platinum layers with an insulating side. Right.
Any other question? Yes?
Okay.
Okay, so let's thank
Thank you.